So for all you wordsmiths out there, rational functions, the root word there is ratio. So it's the ratio of polynomial functions. So rational functions take the form of g of x over h of x, where g of x and h of x are polynomial functions. So a rational function is the ratio of two polynomials. Okay? Okay? And there's some very interesting things that occur with rational functions because of that. What do we have to be always cautious and aware of when we have a ratio?
The denominator can't be 0.
Yeah. So when the denominator is 0, a rational function's undefined. Okay? So there are two things, well, there are a lot of things that are interesting about rational functions, but one thing that we have to be cautious about is, hey, what happens when h of x equals 0? Okay? The other thing we can think about is, what would happen if you have 0 in the numerator? Try again. I think so. 0 over something 0. So the other question is, what happens when g of x equals 0? All right. And so there's a thought that it's okay for g of x to be 0, but when h of x is 0, that leads to some problems. Another thing that you can look at is the long-run behavior. What happens in the long run with a rational function? And we're actually, I think maybe you saw it in Algebra 2, I'm not sure, but we'll definitely look at it today. What happens in the long run depends totally upon how g of x and h and x compare to one another. Okay? So maybe we'll take a... Do you have any questions on that? Like either the idea that we're going to have to look at when h of x is 0, we're going to have to look at when g of x is 0, and we're going to have to look at how the two polynomials compare to one another. We haven't done anything yet, but just conceptually, does that make sense, like the interesting things that might occur? Okay. So we'll start by looking at comparing the two. And if you take a look at 13, we have three functions to look at the long-run behavior. And long-run behavior, that's saying, hey, what's the limit when x gets really big or when x gets negatively really big? So we can look at our graph. We can graph these and see what happens, and then see if it makes sense algebraically, like what we know about algebra. So let's graph them. Let's start with graphing A. And you have to be careful when you plug it in. Whoops. So we don't need that. Make sure you put parentheses around the numerator. And we have x cubed plus 2. So x cubed plus 2 divided by, and put parentheses around the denominator, x squared plus 3. Just out of curiosity, is the numerator equal to 0 ever? X cubed plus 2, is that ever equal to 0?
No. Actually, no. Oh. Yes. It could be.
It could be, right?
No, it could have.
No.
You don't need to. Yeah, you could.
The cube root of negative 2. Cube root of negative 2. So the top can be equal to 0, and that's going to be fine. That's when it's going to cross the x-axis. So we should be on the lookout for that. Can this denominator be equal to 0? No, so that's actually good. It means we're not going to have any problems by dividing by 0, so we're not going to get anything interesting in that regard. So if we take a look, I think I'll start with like a Zoom standard and see how that works. Oh, look at that. There's a little sort of dippity thing in the middle. I'm curious. I'm going to do Zoom decimal and see if I can see anything. Look at that. It sort of almost flattens out a little bit. I think that's interesting. Guess what that value is right there, probably.
0, double 0.
Yeah. it's when y is 0, and it's not a double. It doesn't just kiss. I'm wondering what the x value is. Yeah. Come on, but what is it really? What's the exact value? The cube root of -2, right? It's the cube root of -2. We said that, right? We said that's when we would have a 0 in the numerator, okay? So if we go back to zoom standard, and we could probably zoom out even further if we wanted to, what does it look like this, whoops. What does it look like this function does in the long run? Is it getting closer to something? Yeah, getting bigger and bigger and bigger. What about when it gets negatively big? Yeah. All right. So we can actually look at this function and say, hey, when it gets big, when x gets big, the function gets big. So if I had to write that, I might say the limit as x approaches infinity of x cubed plus 2 over x squared plus 3 is equal to, now this is interesting. There are two ways of writing this. They both say the same thing. One says a little bit more. You can say the limit does not exist. No, I'm not going to say that. Never mind. I'm going to say the limit's infinity. However, you should know that it doesn't make sense to say the limit equals infinity. It's actually saying that the limit doesn't exist. The function doesn't have a limit. If it just keeps getting bigger and bigger, does it have a limit? No. But by saying infinity, we're saying how it doesn't have a limit. How doesn't it have a limit? Oh, it just gets bigger. We can actually look at the function, and we didn't have to look at the graph. What happens when you take a big number and cube it? Yeah, so if I take like 1,000,000 and cube it, like I get like a jillion or something. What happens when I take a big number and square it? It's bigger. Which one is bigger, cubing it or squaring it? So I get like a gajillion over 1,000,000. If I take an even bigger number, I get like a googolplex million over 3,000,000. Basically, the top is getting very, very big, and the bottom's getting big. But when you have a very, very, very big number, and you divide by a number that's nowhere near as big as it, what kind of number do you get? You get a big number. We say that this function is top-heavy. The function's top-heavy because it has an x cubed in the numerator and an x squared in the denominator. The degree is higher in the numerator. It's top-heavy. If you see that a function's top-heavy, that will help you determine what the limit is. The limit's going to be infinity here because it's top-heavy. Just out of curiosity, what would happen if we did a negative big number? Well, let's think about it algebraically. If you take a negative big number and cube it, what do you get? A negative, big or small number?
Big negative.
Yeah, really big negative number. If we take a negative number and square it, a big negative number and square it, positive and big, but the cube's going to be bigger. But the important thing here is it's negative on the top. It's like a negative gajillion on the top over positive 1,000,000. The lions go out and you get a ga over m. No, that's not true at all. But you get a big negative number. The important thing is you get a negative over a positive. And that's what the graph said. Is that okay? Do you want to ask a question? All right, let's do the next one without graphing it first. All right, so first of all, when's the numerator going to be equal to 0? Say it loud and proud, Peter. When what's -2? Perfect. When's the denominator going to be equal to 0? Never. All right. If we take a really big number and plug it in, what kind of number do you get on top? A big number, plus 2. All right. If you take a really big number and put it on the bottom, what kind of number do you get? An even bigger number. All right. what happens if you take a big number and divide by a much bigger number? Like if you have like 1,000 over 1,000,000. You get a small number. We say that this function is bottom heavy because the degree in the denominator is greater than the degree in the numerator. It's bottom heavy. It's going to get closer and closer. Now when you say smaller, what do you mean? Yeah? Yeah, it's going to get closer and closer to 0. So look, we didn't even graph it yet. Now let's go back and graph it and see how we did. We have x plus 2, the quantity, on top, and we're going to divide by x squared plus 3, the quantity, on the bottom. Make sure you have all those parentheses. And I'm going to do zoom standard again. Oh! Maybe I'll do zoom decimal. I don't know how yours turned out, but zoom standard seems a little too far away. So here I have a function that looks like if I go out in the negative direction, it gets close to 0, and if I go out in the positive direction, it looks like it gets close to 0. That function, the y values get closer and closer to 0 as x gets bigger and bigger. To write it, I would say, hey, the limit as x approaches infinity of x plus 2 over x squared plus 3 is equal to 0. And I could also say the limit as x approaches negative infinity of x plus 2 over x squared plus 3 equals 0. And the graph tells me that, and I know algebraically because I'm reasoning that a big number over a much bigger number is close to 0. And you could do the table too, right? Or, I mean, there's so many ways of doing it, right? If you really wanted to, you could do second quit. You could do vars, y-vars, y1 and say, hey, what happens if I plug in 10? Oh, I get a small number. What happens if I plug in 100? Ooh, I get an even smaller number. What happens if I plug in like 1,000? I get a really small number. Like, are you convinced that when it gets bigger, we're getting close to 0? Say yes, Rafi. Good. She shook her head. Okay. I wouldn't want anyone to think you didn't say yes. All right, and then finally, what would you say about C? Top heavy or bottom heavy? Is the top really that much heavier?
Not by much. It depends.
All right, so let's say if we take like a number and cube it, a big number, like 1,000,000. You cube it, you get a gajillion. So on top, what do you get? 3 gajillion plus 2. Now the 2 doesn't really matter, but it's fun to say it. In the bottom, what do you get? Plus 3. See, it's fun to say, don't you think? What do you get when you take 3 gajillion over 2 gajillion? Mm-mm. What do you get if you take 3 gajillion over 2 gajillion? Whoops. I got a little messy. Oh my goodness. Okay. I got a little excited with my zeros there. What happens to all those gajillion zeros? They go, and you're left with 3 over 2. And it ends up that anything that happens afterward doesn't really matter. Like the plus 2 doesn't matter. As a matter of fact, if I had 3x cubed plus 2x squared over 2x cubed, you might think that the 2x squared would be important. It's not. In the long run, anything less than the leading term doesn't matter. It's totally inconsequential. It doesn't matter if we add 2 or 5. It doesn't even matter if I did plus 1,000,000. What matters are the leading terms. And in this case, we would get 3 gajillion over 2 gajillion. And in the long run, it would get closer and closer to 3 over 2. Let's see it. See it to believe it. What do we have up top? 3x cubed plus, here, I'll even do 500. Over 2x cubed And I won't even add anything to the bottom. All right. If we take a look at that in zoom decimal, oh my gosh, I don't even see anything. All right, I'll give it a shot. Nothing. Well, I got something, right? But I'm going to have to zoom out a lot, I think. Zoom 3. Where'd the function go? It's because I added 500. I'm such a knucklehead sometimes. Oh, I added 5,000? All right. So I'm going to go from like negative 1,000 to positive 1,000. And see what I. Thanks. You got it in Zoom Standard, and it totally fits. Oh, I'm such a knucklehead sometimes. Hey, look at that. I got 2 pieces of it, and I think what I'm going to do is I'm going to take my x values and go from like negative 30 to positive 30. And here it is. If I were to go and trace, here's the little X point, and I'm coming down. It looks like maybe I'm getting closer and closer to the x-axis, but I'm really not. As a matter of fact, look at my y values. They're slowing down. What are they getting closer to? Yeah, 3 over 2, 1.5. You keep going out. All right, so if you have a function where the degree is the same in the top and bottom, you can look at the ratio of the coefficients. Okay? I'd like to look at zeros and asymptotes and then talk about homework from last night. Do you have any questions about long run behavior? You can use your graph. You can use a table. You can plug in values. Or if you don't have those available, you can actually ask yourself, is it top heavy? Is it bottom heavy? Or if the degrees are the same, what's the ratio of the coefficients of the leading terms? Okay? Let's look at 3x plus 1 over x minus 2. (3x plus 1 over x minus 2). All right, first question I'm going to ask you is long-term behavior. Is it top heavy or bottom heavy? Same degree. It's neither. Okay? They're fine. The heavy means is the degree higher in the numerator or denominator. They're the same, so since they're the same, how can I figure out where this function goes in the long run? Michelle? 3 over 1. So in the long run, this function is going to get closer and closer to 3. Okay? That's out here on the left and right. It's going to get closer and closer to 3. So that's something nice to look at. The 2 other things that we said we would be concerned about is when is the numerator equal to 0 and when is the denominator equal to 0. The numerator equal to 0, Danny said, that wouldn't be a problem. That just tells you where the zeros of the function are. So when is 3x plus 1 equal to 0? Negative 1/3. All right, now, we know we're going to have a problem when x equals 2. What sort of problem is that from Algebra 2 when there's a 0 in the denominator? It is. And how does that show up on the graph? Yeah, what do we call them? No. Mo? Okay, and if you put your adjective in front of it, vertical asymptote. We get a vertical asymptote. Okay? So look, we haven't even looked at the graph. We already know in the long run it's going to 3. It has a 0 at negative 1/3, and there's going to be a vertical asymptote at 2. And now, let's see how we did. You excited? 3x, was it plus 1? Over x minus 2? Alright. And I'm going to do zoom decimal to start. Oop, there's negative 1/3. No, I didn't get the rest of it. Bad choice. Zoom standard. Oop, there's negative 1/3. And there's that vertical asymptote. And if I trace out on the function far enough in either direction, it gets closer and closer to... Good, thanks, Keith. That was nice. Very enthusiastic. Say again? Whereas the vertical asymptote's right here at x equals 2. And here I will... grab that. It's the big hole, right? It's the big gap.
Yeah.
So there's the vertical asymptote at x equals 2. Okay? So as the function gets closer and closer to that, it goes to negative infinity and positive infinity, and there's like a big hole in the graph. Okay? You want to ask a question about zeros, asymptotes, or long-run behavior? All right, I have one more cool thing to show you. At least I think it's cool. I don't know what that means. All right, let me think. No, it's the limit. It gets closer and closer. It will never reach there. Your calculator, you will fake your calculator out. If you go far enough, your calculator is going to say, you know what, 2.999999999. I'm going to call that 3. If you go out to like x equals 1,000, and you don't have to do it on the graph. You can just go to y1. You can go to your home screen and type in vars y1. Do y1 of 1,000. Your calculator is going to say 1.5. Your calculator just can't deal anymore. Now it's not true. At 1,000, it's not actually equal to 1.5, but it's so close that your calculator can't deal with the decimal approximation. Let's see, x squared. Plus 6 minus 5x plus 6 for x. X, hold on. Don't tell me. Okay. It's minus 1. Okay. Hey, zeros? Where do zeros happen?
3, 1.
No.
Which zero? Oh, I get it.
Where do zeros occur? I know Peter knows, but I don't want. Well, so don't tell me where they occur, but when. I should say, when do zeros occur in a rational function? Numerator equals 0. Numerator equals 0. So the question is, when is x squared minus 5x plus 6 equal to 0? And Peter, I think you already factored it. What'd you get? So it's x minus 3, x minus 2, which would give us zeros at 2 and 3. So x equals 2 and 3 are going to be zeros. When do we have problems in the denominator?
At 3 and 1. But 3 is...
Something weird's going on at 3. Because I have a problem at 3 and I have a 0 at 3. You want to see what happens at 3?
Yeah.
Check this out. You're going to like this. No, really. It's cool. Alright, so you don't believe me. X squared minus 5x plus 6 all over. Now we have to be careful here. Quantity, x, what, minus 1, x minus 3? Is that what it was? And quantity. So it's a double quantity in the denominator. Oh my gosh, really? Is that better? Alright, I'm going to try zoom decimal. Oh my gosh! We knew there was going to be a vertical asymptote, right? What happened at 3?
Whoa.
Oh my lord.
There's nothing there.
It's crazy. It's not a vertical asymptote. It's not a zero. It's just missing.
Zoom in. I need more
Weird.
All right. I think it's awesome. Oh no. Okay, hold on. Trace 3, enter, zoom in. It's still missing.
We need to see it closer.
Oh, I know your ways. So that's really, I think, interesting. Have you ever seen a missing dot before on a graph? Do you see that in Algebra 2 or no? No. Okay, so what ends up happening is in the top you get x minus 2, x minus 3. In the bottom you get x minus 3, x minus 1. What happens to the x minus 3s? They cancel, and because they cancel, it creates not a vertical asymptote, but we call it a hole, or a removable discontinuity. That's a big fancy word, yeah. All those syllables. Discontinuity means you have to pick up your pencil. Okay. Removable means that, hey, we crossed them out. We removed that discontinuity, but it left a hole. Okay. So the difference between a hole and a vertical asymptote is whether or not you can remove it with algebra. Okay. Now, removing it, you still get that little hole. X minus 1 didn't get removed. That's just called a vertical asymptote. That's a different kind of discontinuity. We had to pick up our pencil here because it was a big asymptote. We had to pick up our pencil here because it was a tiny hole. Asymptote. I think I did that right. Oh, come on. That was worth coming to class today, don't you think? Yeah, that was cool. All right. Homework. What do we got? Couldn't do it. Another one.
35.
No, still couldn't do it. All right, which one was 35?
It had like, it didn't have any zeros. It had like.
All right, so it was a graph, and it had a bunch of 4s.
Yeah.
Was it like this?
Yeah, like all along y equals 4 at negative 3, negative 1.
All right, so wait. At negative 3, where else?
Negative 2.
Negative 2, and at 1.
And it crossed over on the line.
0, 10.
Oh, okay, sorry. So I messed that. That my graph is totally wrong, isn't it?
It's negative 1.
Oh, at negative 1. All right, so it did something like this, and it crossed at 10. All right, so guess what? This graph would look awesome if it didn't do this, but if it did this. Don't you think? If it had zeros at negative 3, negative 2, and negative 1, what did I do to the graph? Shifted it down. What did I do to this graph? We'll talk about, you could say I shifted this one up. That's fine. I shifted this one down 4. So this would have an intercept not at 10, but at 6. I've totally changed the problem. Wasn't that sneaky of me? All right, but so let's see. You can't do this one, right? This one leaves you, like, totally confused.
So you're allowed to do the whole thing.
Oh, no, we're not. Oh, no. Yeah, I couldn't figure... what was I doing? I don't know. This one's like... Oh, yes!
Look at the Kool-Aid guy.
Wasn't he a pitcher? And he had...
Shorts.
Did he have shorts?
Get a vest.
Big like shorts.
A vest? Did he have a handle on him?
Yeah, he did him this. Yeah. Did he also carry around a glass of Kool-Aid?
Yes, he was a glass of
He
Kool-Aid.
was a picture Kool-Aid, didn't
He drank himself.
That's weird.
That's disgusting. It's like drinking your own
And he
blood.
encouraged other people to drink him too.
Yeah. Ugh. All right. All right. So,
Things.
play with me here. For this one, give me, so it's going to be a cubic, right? All right. Rafi, give me one of the factors, because I know I don't know what you're doing, but you're doing something. Give me one of the factors. I'll come back to you. Good, no, but give me a factor. Mo, give me a factor. Oh, come on, Mo, you have all the right answers. Jen, give me a factor. No, that's not a factor. Michelle, give me a factor. X plus 2 is a factor. Now watch what happens. Oh, yeah, when you say factor like that. Rafi, give me a factor. Jen, give me a factor. Do you agree that those are factors? Yes, okay, fine. Now, it's a cubic, so it has some k value, right? And what I need to do is I have to make sure that the k value gets it to go through this point. What's that point? Corinne, what's that point? What, 6? Are you whispering? What is it? No, say it. What is it? Yeah, 6. What? Sorry, 6 is a number. I'm talking about a coordinate. What coordinate is that? 0, 6. If I plug 0 in, I want to get 6 out. So k, 0 plus 2 is?
2.
0 plus 3 is?
3.
0 plus 1 is?
1.
Hey, what's k equal to? 1. It is not. 6k equals 6. It's equal to 1. So, in other words, this graph here is the graph of x plus 2 times x plus 3 times x plus 1. But Corinne, that's not the graph they gave us. Because, right, you were saying, can we just move it down? And I said, no, we can't. No, I know. I'm just saying, it was a great question. I'm like...
It wouldn't fit down me.
So, if we know the equation to this one, the oh yes one that we can do, well, Monty... It was good. I'll keep you around just to do that next year. All right. What's the difference between these two graphs? Shift. How much? Which direction? How about this? Is that cheap? Yeah, it is. Totally is, right? But does it work? Yeah, it does. So, look, the fact of the matter is, now I know Corinne asked it, but a lot of you had the question. I can't do anything, or it's going to take a whole lot of work if all I know is where the function is equal to 4. I mean, that's just not all that helpful to tell me when the function is equal to 4. But if I know when it's equal to 0, it makes it a lot easier. So if there's something I can do to change my perspective, I'm going to shift it down, figure it out, and then just shift it back. Did you have a question or do you have an answer? Okay. Anything else from last night? What do you have, Monty? Monty, then Evan. Which one was that? Was that another graph one?
It gave you words and it wasn't you.
Oh, what are the words? What are the clues?
Least possible degree through the points -3, 0.
-3, 0.
1, 0.
1, 0.
And 0, -3.
0, -3. All right, so I know that, let's see. I know that it has 2 zeros. So what's the least possible degree it could be? 2. So it's going to be a quadratic. So what are the factors? Give me a factor. Monty, give me a factor. X plus 3. Sam, Roseanne's, give me another factor. X minus 1. That's the foundation, the basis for my quadratic. Now, I have to put a k out in front, a constant of proportionality, because I also need it to have a y-intercept of -3. Okay, so I'm going to use what I started with. I'm going to plug in -3 equals k times what 0 plus 3? What 0 minus 1? Oh my gosh, k is 1 again? Oh, that's so annoying. I know, but like from a teacher perspective, it's annoying. All right. And by fun you mean easy. So,
no matter what.
Sorry, it'd be like a number system that only included 0, like 0 plus 0, 0 minus 0, 0 times 0. Oh, we'd have a problem though. 0 divided by 0 is no good. No. only has 0. There are no other numbers. It's just 0. I guess you could have... Yeah, all right. Evan.
No, that's what I was just saying.
Oh, really? All right. Max. Keith. Miles.
14.
All right, Monty, what do we have to do?
Maybe find the window.
Oh, gosh, these were hard.
Yeah.
Weren't they? How to use our calculator? No, I'm not being facetious. It was hard. Tell me this, Monty, what's the function that I'm looking at?
U of x equals 1/8 x cubed.
Hold on. 1/8 x cubed.
And v of x equals 1/8 x times x minus 0.2.
So I have to look at them in the same window and hope I can get them to look different. 1/8 x times the quantity. Oh my gosh. X minus 0.01 quantity squared. We have to do a zoom standard. There's x cubed, or 1/8 x cubed. There's the other one. Should I turn the other one on to Bubble Guy? So here's the first function. Now look at Bubble Guy. Bubble Guy, he goes off a little bit right here, and off a little bit right there, but for the most part it looks almost the same. So are they the same graph? Probably not, right? And we need a good window to see that they're not the same graph. Thoughts or ideas? Did you come up with something that we could look at?
I did.
Make y really, really big.
So if I do like...
I did 5.95. And then 26.
Hold on. What happens if we look at from like -2 to 2? Is that not enough zooming? Oh, I didn't zoom enough. Alright, sorry. So, well, I'm starting to zoom enough. And, is it true that if I... Okay, you don't care. You could totally look at the table, right? You can go, hey, your homework's 9-4, not 9-3B, and I'm going to still play with this for a little bit. -2. Oh, I totally missed the graph. No, I'm doing horrible with this.